followed by a panel discussion. So let's start now with Jim Kim on interpretability. Wow, what now?
Thanks, Sammy. This is work with a lot of awesome people inside and outside of Google, listed here, and I'll give a talk on this mysterious title, interpretability. What now? Last couple of years has been an amazing ride for field of interpretability. There are a lot of papers published, there's workshops, there's symposiums, but I still see this as a drop in the ocean. Because interpretability is such a complex problem. We have all the problems that traditional machine learning folks have, computations, all the robustness and whatnot. But in addition to that, we have this another complex thing that we have to worry about called humans. And in fact, they're so complex that there's a whole field for it. It's called psychology or cognitive science. And perhaps this complexity is what keeps people interested in the field. But this is also why we need to decide where we're going in this field. Because we have to row in the same direction to get somewhere. If we're all rowing in different directions, we might just spin around in a circle and not going anywhere. And it's important to mention that interpretability is not a new problem. Back in the 80s, expert systems, we already had thought about this problem of how do we communicate something complex to humans? And I think it's reasonable to say we haven't quite solved that problem yet. So today I'm going to talk about, first, where are we going? And second, where are we now? What kind of method do we have? Does it work? Does it not work? If so, when? And I'll suggest an idea how we can do better. Then we'll come back to that idea and see, okay, now I have this idea, how can we do even better? And finally, we'll end with some remarks on what sort of things we should watch out in our journey. So first, where are we going? Unlike traditional machine learning problems or supervised problems where the community generally agrees that, accuracy, while not perfect, is generally the good direction to head down to, we don't have such a thing in interpretability. And because it's complex, we have to ask a little harder question. It's hard to have mathematical definition of interpretability, and that's what Bin Wu was talking about. We need to define interpretability under context, under condition, on the user, who are you serving for. So we have to ask this harder question that involves value judgment. What are you trying to do? Like ultimately, what are you trying to achieve? What do you care? So your goal is your goal, but I would like to share my goal. Love to hear what your goals are. But my goal is to give people a tool so that they can help themselves to use machine learning more responsibly. I really believe that a lot of people want to do the right thing, but sometimes maybe they don't have a tool for adjusting, analyzing this new term they added in the loss function. What does it do? What kind of feedback loop does it create? They just don't have the right tool. So the goal is to give them that tool so that they can use machine learning more responsibly. And these are not complete lists, but one, the tool should help you to make sure that your values are aligned, such as fairness. And the tool also should help you to confirm whether your domain expert knowledge is reflected when you want it. And I particularly care that this works for everyone. Because when medical domain, like high-risk domains, we have domain expertise like doctors who holds critical knowledge about how to make the right decision, but they may not have computer science background. It's rare to see someone who has PhD in computer science and MD. They do exist. There's coupling in the brain, but it's rare. But those are the times when interpretability becomes most important. Also, society point of view, this powerful tool called machine learning, anybody should be able to leverage it regardless of where they went to school or whether they went to college or not. It's also important to think about what are not our goals. It is not about making everything interpretable. There are plenty of applications where you just don't care about interpretability. You don't need it. Then, don't worry about it. It's also not about understanding every single thing about the model. I think about interpretability as a translation problem. I speak two languages. I speak Korean and English. And there's some words in Korean that I cannot quite translate in English. But I can kind of describe, get around it, and kind of get the meaning across. It's not exact, but it's useful. And that's how I view interpretability method. You're trying to map these two things. It's not exact, machine language and human language, but as long as it's a useful tool for you to achieve the goal, it's meaningful. It's also not about against developing highly complex models. It just means that we have more work to do. And it's also not about, in my view, gaining user trust or purely for fairness. In fact, I think an interpretability method that is really useful is to convince you to not trust the model when that's the case. In fact, there's this paper that is mind-blowing. I highly recommend you to take a look. This is a Nature published article a couple months ago about how they trained the hip fracture medical image and thought that it was reading something meaningful from the medical image about whether this patient, something about this patient, whether this patient will deteriorate or not. But it turns out that it wasn't. It was actually paying attention to the machine that the image was taken, the model of the machine, and all these other confounding factors, not the image. And in this case, what interpretability method should do is say, well, I don't know what this model is doing. It's doing this weird thing. And that's when it's not about trust. It's about helping you to decide whether this model should be used in real application safely or not. So I gave you a direction that at least I would like to head to. And let's now talk about where are we now? What kind of method do we have? There are lots of different kinds of interpretability method, but just like we knew, I'm going to talk about post-training interpretability methods. What does that mean? It just means you have a model. You cannot change the model. And your goal is to do best as you can to interpret this model. So to be concrete, let's say you have a model, like your network, takes an image, and it predicts that's a junco bird. And you want to answer, given this model, give me the evidence of prediction. In other words, why was this a junco bird? So the most popular method that we saw a couple of times in the past couple of talks is saliency maps. What does it do? Well, it simply takes a lot of methods are based on this first order gradient. So take probability of, say, junco bird, and take a first order gradient with respect to every single pixel. So that means intuitively, if I change this pixel a little bit, how much would the probability of junco bird change? If it changes a lot, it's an important pixel. If it doesn't, it's not an important pixel. So that's cool. So again, the promise of this method called saliency maps is that these pixels are the evidence of prediction. So then we can ask this sort of really simple sanity check question, which is, if it's evidence of prediction, then when the prediction changes, then the explanation should change. And you can think about an extreme case, when the prediction is random, explanation should really change. So we test that. This is work with awesome PhD student at it used to be at Google, Julius. So now what we did is the following. We took a beautifully trained network, takes that picture, predicted the junco bird, and gives us this saliency map. Now the saliency map, looking at it, kind of makes sense. The belly of the bird is kind of important. The cheek of the bird is important. Okay. Then we copied this network, and we start randomizing the weight, the learned weights, from the top layer in a cumulative fashion all the way to the bottom layer. So what I did here is I just messed up the perfectly good-looking network. Now completely, the prediction is completely random. It's a garbage, right? So you would think that explanation should change. It doesn't. Now, you may argue, well, but these two pictures are technically different. The sky looks a little darker here. But remember, the final consumer of your method is human. And as a human, I don't know if I will draw a completely different conclusion based on these two pictures. Belly, still important. Cheek, still important. And we do this for a lot of different methods, including my own work, starting from the logic layer, just logic layer, and in cascading fashion all the way down to the most bottom layer. So here, you're looking at completely randomized network. And as you can see, some method barely change. And here's some more recent picture that Julius has put out, some of the more recent work, again, including some of my work. And remember, this second column has random prediction. It's pretty similar to the first column. So we're shocked by this. And we're like, okay, well, what about different kind of randomization? What if we train a network with random labels? So we did that. This is a network trained with the correct label in MNIST. This we trained with random labels. Some method, you can still see the digit 0, but it never learned what 0 is. And the vanilla gradient seems to be doing the best. And a lot of methods that we listed out here are based on doing some fancy things on top of vanilla gradient. So what is this? What can we gain from these results? Well, I think this is showing something that I repeatedly see in my work. Oh, yes?
Did you look at data sets which aren't really foreground background?
Such as?
So even CFAR is a little bit less foreground background. There is something in MNIST, and in, I don't know if this was like the CAV or something. There's definitely a central object which is being detected in like the in the case of the bird image, it was a fuzzy green background.
Yes, so the work that benchmark data set that I'm about to talk about might get you to that answer. So it's like that we're just biased to look at the center object, right? Yeah. Let me answer that question when I get there. Good question. So what is this? Well, confirmation. Oh yeah, yes.
Sorry, another question. So, I mean, pretend, say, a 3-layer network, right? That detect, which was semantic. So you could look for small curves, and then these curves at the next level they form a loop, and then finally I label it as a 0. Randomizing the last layer only tells me that I don't know it's a 0, but you're still detecting the features. So the feature information is not lost when you are randomizing the last layers of the network.
This is getting to an important point. Let me answer the question. So first of all, this is 0. It never, well, actually, let me answer it this way. The promise of the saliency map is evidence of prediction, right? It's not, the promise is I'll give you 10 things and one of them might be what caused the prediction. Not that. It's saying, what I gave you is why this picture is a bird, right? And I think what you're getting at is, yes, it might extract some features, and maybe saliency map is showing that feature that might have been used for prediction, but that wasn't the promise of the methods. In other words, think about it this way. Like you have a medical image, right? And your cancer cell got into the doctor, and doctors are looking at the saliency map, right? Do you think if the saliency map is not promising either getting you those high recall or high precision. It's just getting you something, right? Some feature that might caused the prediction. That's not really what the evidence of prediction is, right? It should give you the smallest and sufficient set of that caused the prediction.
Isn't the problem in that you only look at the first order, like the effect of a single pixel, and not the effect of sets of pixels?
Yes.
And the significant could be a combination of features.
Yes, totally agree. So I will actually talk about it. It's a really great segue to my next work, which does basically that. Cool. All right, so let's talk about this confirmation bias, because I think it's one of the most important things when we work on interpretability method. When we see these pictures, we like it. We expected to see a bird. So we saw a bird and we liked it. And for all these years, we're like, yeah, we see a bird. This makes sense. This is a bias. It's very well studied in a lot of other fields. And that's what I think we are seeing here. We really should have been passing this test a long time ago. And coincidentally, a couple of other papers discovered similar symptoms. One beautiful paper mathematically proved that some of these methods are actually just reconstructing the input. It has nothing to do with prediction. But some papers went out of their way to test this with human experts. And they show that, yeah, they do help human experts. So why? We don't know that yet. Something in here is helping human experts, but we need to do more study to figure out what that is so that we can amplify that. Recent work, elegant work by Sanjeev Arora from Princeton had suggested simple fix, elegant fix to pass this test. It is to be seen to check whether this method also formulate a faithful explanation. That's TBD, but I think it's a great start. So again, this test, it's kind of dumb test. I think it's such a low bar test. We should be really passing this. So then next step we thought about, can we put methods in a harder test? So this is work with Cherry Yang at Google Brain. The goal is to make a benchmark data set so that any interpretability method can evaluate that, because in this case we have ground truth. We know exactly where in the image should be important. So how do we do that? Well, it's pretty simple. We get scene data set, forest, kitchen, stadium, and then we get an object from MS Coco, because it's a nicely chopped out dog, chopped out the backpack, and so on. So it's a thing. Then what we do is we paste this thing in every single image for all classes, uniform. So if I were to classify scenes, the dog should give you no information. So we know that dog, the attribution methods or saliency maps should not highlight the dog. And that's what this says. We can go one step farther, and we can do relative testing too. We can put this dog in some of the classes, like forest, and not the others. And that means dog will give signal to what the forest scene is. So we do that too. And in particular, I think it's important to notice what we are focusing on here, what we are trying to measure. We believe that interpretability method makes pretty much similar types of mistakes as machine learning models. And here in this work, we are focusing on false positives. Interpretability method said, I'm important, but model doesn't think so. So under that, we suggest 3 metrics. I'm going to talk a little more about the first one, but quickly the input dependence rate and input independence rate. Independence rate is input dependent is that if I change the input, the image, in a way that it matters, then it should really change. Input independence rate is kind of an adversarial patch where we initialize a pixel with a dog, and we gradient descend such that that patch of pixels shouldn't matter to neural network. And we see that the attribution method still went crazy on the dog. And answer is yes, it does. But, so the details are on the paper, but let me talk a little bit more about model contrast score. What this does is, we made this data set. Remember, we paste the dog, so we know exactly where the dog is. We trained 2 models, one to classify the scenes, and the other one to classify the objects. So I only show you the dog, but in our data set, there's a dog, there's backpack, and 10 different classes. And what that does is, we expect where the object is should have a high contrast in these 2 models, right? Because one, it's just looking at the scene. The other one, we know that the dog is important because scene is uniformly distributed. Scene doesn't give you any information about what the object should be. So we did that, and we got scores. These are popular methods. GradChem does pretty well. SmoothGrad also does okay. TCAV, which is the method I'm about to talk about, does also okay. We are open sourcing soon data set and models and everything on this Beam data set once we get license issues sorted out. So that's harder. Yes?
Sorry, I'm a little confused. So what are these methods? These are interpretability methods? Or these
the GradChem, vanilla gradient, SmoothGrad, integra gradient, saliency methods.
Oh, they're all saliency methods.
Yes.
So they all output some subset of the pixels.
Yes, except TCAV, which is a global method.
But then how do you compare? Like, what's the exact metric?
Average. Average attribution. So I have a lot of dog pictures and scene pictures, right? So forest and forest plus dog, and I have a lot of them. And I measure how much contrast is in each picture, and I average them over, and that's this number.
Okay. And I guess I'm trying to interpret what does 0.2, 0.1, how good we are at this.
I see, yes. So that's a more complicated question. Higher the better for now.
Okay.
The max is 1.
The max is 1. Okay.
Yes.
Is it all with respect to the same classifier? Because maybe what you're detecting here are issues of the classifier and not some general issues of the interpretability method.
Good point. So this is only thinking about these 2 models that we trained. It's not perfect. It's not going to be general overall. However, I think it's at least better than doing nothing. It's limited. Also, it's a semi-natural data set. So it's not completely natural, but I think it's a great start. Once we pass this data set and we're nailing it, then we go to the next level. Yes?
Sorry, just another quick question related to Shai's question. So what if I just do a segmentation? I label and segment together. That sounds like I will pass this test perfectly.
You segment the dog, okay,
Yes,
and then.
I label it and I segment. Yes.
But then once you segment, you have to attribute correctly, right?
So yes, I have per pixel.
Yeah, no. I mean, if you have a perfect segmentation method, as far as I know, superpixel method doesn't like exactly carve out the dog. I find it difficult to. Maybe you can do it. If you can do that and you can appropriately put the right number, then I think you're good. However, I don't think you will be able to pass or like do all well in these 3 metrics. Maybe you can.
But yes, but I guess it sounds like it's a little bit fishy that if I have a perfect segmentation algorithm, I can pass all the interpretability results. So I start with a non-interpretable segmentation algorithm, segmentation model that works perfectly, and then I can pass all the interpretability tests. That sounds.
I think a lot of interpretability method actually uses segmentation, like Lime and Sharp actually super pixel segment and then attribute. I haven't seen a really good segmentation method that just carve out the dog perfectly and attribute it. If you can, I think that's a great start. However, I don't.
Then we should work on segmentation. So
even if you can, I think these 2 measures are measuring slightly different things. So for example, I don't think it would pass the input independence rate. What it is the following. I have a scene, and I put a dog in somewhere, and then I gradient descent only on the dog side to make sure that that part of the pixel, that set of pixels, don't matter to the network decision. So it's adversarial in different way, right? That's such that it doesn't matter. Let's say you did a perfect segmentation on that, then you would have to put something on the dog, right? If you can put the right number on the dog, I think that you're good. But I think it's a little harder than what you're describing as. Cool. All right, so we talked about this, where are we now? And this method, while it's helpful sometimes, may not be working in the way that we expect. So how can we do better? So again, the problem here is post-training explanation. I changed the example. Now you're looking at a cache machine picture, passes through the neural network, says it's a cache machine. The goal is to answer, why was this a cache machine? Now let's stare at this saliency map that we just talked about to help us think about what do we really want? What's the goal? As I stare at this picture, you see this human in front of the cache machine that's kind of highlighted. And I start to wonder, maybe the human mattered, human concept mattered. The fact that human was in the picture helped predicting cache machine. And I also noticed this weird thing, this cart behind the human, the wheel is highlighted for some reason. And I want to know whether that mattered, because that sounds more problematic. And if there were a thing, then I want to know whether which one was more important. If it's a human, that's maybe a little better comforting than if it's a wheel, right? And I would also like to know if it's just this picture or all cache machine pictures. The problem is that you can't really express these concepts as a set of pixels, especially across many images. And I think it's getting back to your point that maybe it's some higher level thing. And also, if you had these concepts in the input feature, then you're fine. But you didn't. I just came up with it, and the model is all that you trained. So wouldn't it be great if we have a quantitative way of measuring how important these concepts are? So that's what we did. It's called testing with concept activation vectors. The goal is you give me a concept that you care, such as gender or race. Then if it mattered to the model, then I'll tell you in number between 0 and 1 how important the concept was for the prediction. So giving you a slightly different example, running example throughout the talk is going to be our zebra. And I'm interested in whether this stripeness concept matters for predicting zebra.
Sorry, what's the definition of a concept?
It's coming in the next slide. So what is a concept? Like you talked about this concept thing, it sounds good, well, what is it? Well, we define concept as a vector and doing the simplest possible thing. What do we do? Well, to define concept, you need a couple of examples of concepts, like striped pictures, and you need some random images. Then you pass these images into the network that you're interested in investigating. And in a layer, I'll talk about which layer, how to pick this layer. In a layer, you gather all the activations of these concept pictures and random pictures. Then we do the simplest thing. We just train a linear classifier, find the vector that's orthogonal to that classifier, and that's your concept vector. What is it? Well, it's just a vector that points from random direction to concept direction. This is not new. Word-to-back paper already talked about gender vector. Lots of other papers talked about this existence of this vector, and that's what we call concept vector. Yes?
And I assume that in practice you are using images from the same distribution.
It doesn't have to be necessarily, but it would have to be. It is not completely something random. So, for example, that's actually an important
Because, like, for
question in
example,
practice.
here, everything on one side is just a line drawing. Everything on the other side isn't a line drawing. So,
I see. You mean between these
Between
two?
these two, yeah.
I see. Oh, I thought you were asking a different question. I mean, yes, yeah. This has to be no line. Or you can have some line. There's a reason why this guy isn't here. But as long as the majority of them are.
but it's from the same. It's from the same input distribution.
Yes, it has the random images. It's better if it's roughly from training distribution. Yes, good point. It's a really important point in practice. Because then you can learn just better vector. You just learn a tighter boundary. Yes?
So the concept is relative to your random class. So if I choose a different random class, you can have a different concept.
I love that question. So we do many times, and we do a simple statistical testing based on that. I'll get to that. All right. So we have a CAV. We have this vector. Now it represents a concept. Now how do we get this quantitative measure that I talked about, or TCAV score? It's also really simple. To get TCAV score, we take the probability of a zebra, and we're taking the directional derivative with respect to that vector that we just got. So what is this? Well, intuitively, what it does is, if I move my picture to be more like the concept or a little less like the concept, how much would the probability of a zebra swing? If it swings a lot, it's an important concept. If it doesn't, then it's not an important concept. And then we do this for many zebra pictures. Then we just take an average. This is, if you had 100 zebra pictures, how many of them having zebra concept was positively contributing prediction of that class? This is simplest possible way to define TCAV score. You can put an inequality, you can do negative, to do all sorts of things that fits your bill. But this is just simplest thing that I thought of first time. Yes?
And do you only use the sensitivity, or do you use other methods in order to measure the saliency?
What else?
So, for example, right, like if I take a zebra picture, I change it to half the zebra picture by dimming the pixels. That doesn't change any of this. So maybe the gradients you might see are exactly zero.
Oh, I see. I think you can do fancy other things to make sure that things are even tighter. We don't do that in this basic TCAV work.
So, right, so I mean, you talked of several methods for measuring saliency, but you only use the gradient.
Yes, it's a great point. So you can combine, say, integrated gradient or sharp value to do concept attribution. It's just like a kind of, I think of this as a canvas, like a vanilla method that I put it out there. It's a simple, and people can do sort of smarter things. All right, so we have this simple TCAV score definition, and now I'm going to get to Binwoo's question. We happen to have the same name. How do you validate this CAV? We're going to do a small, cute statistical testing. There's also a qualitative way to convey and confirm this concept vector, but I'm going to talk about quantitative way. So we talked a lot about adversarial example in talks before me today. How do we know? We know that high-dimensional space, things are a little funky. So how do we know that we're not getting this high sensitivity by chance? So here's one way to safeguard this. Not perfect, but one way. So just like Binu said, these set of pictures are random, and therefore we can have any set of as many as random images we want. From each set, we're going to get a CAV that are slightly different, perhaps. From each CAV, for a given target zebra, we're going to get many, many TCAV scores. And you can view this as samples from a distribution. And if, in fact, the stripedness was important for zebra, you're going to see something Gaussian nice like this. So most of the time, in a lot of CAVs, stripedness CAVs, the TCAV score was high. And then what we do is we compare that to random CAV, where random CAV is where this is random and the other one is also random, but similar training distribution. And we show that the mean of these two distributions are statistically significantly different. Because if not, you're in trouble. It's as good as random, then you might as well not use it. So if a concept does not pass this test, then we say, oh, sorry, you gave me this concept, but maybe model didn't use it. We can't give you an answer. That's how we do the test. It's not a perfect test, but a test. Okay. So I talked about this TCAV work, but why should you care? Well, I think it's useful in a couple of settings. At first, when you have, after the training stage, a lot of times you may have this like intuition. You saw a mistake, and you're like, oh, maybe that was the issue. And you have hypothesis, and you can basically have hypothesis testing with the machine learning, already trained machine learning in the loop. And of course, if you input feature did not include it, oops, you don't have to go back and retrain the model. You just use this and try to get the answer for the question. So some results. How am I doing on time?
You have 13 minutes total.
Great, okay. So first, it's a different sanity check experiment. But we do sanity check experiment in this case. In other words, if we know the ground truth, what would the important concepts are, then would TCAV match? Because if it doesn't match, then we're in trouble. So we did this test. We had 3 class images, like taxi and soccer and cucumber, I believe. And then I programmatically added this caption, potentially noisy. And what I did there is essentially creating 2 concepts in this image concept and caption concept. So I will create a scenario where the model can use one or the other. How do I do that? Well, I can create 4 different data sets where sometimes I give perfect caption. So whenever there is a CAV, I write CAV. Sometimes I give 100% noisy caption. Whenever there's a CAV, I write like tiger or something, and it's equally distributed across the classes. And this is different data set is just to train different models that does different things. And how do we know the ground truth? Well, you can test the model that's trained on this data set with a data without a caption. So if the model did use and only relied on caption, it's not going to do well because I didn't give you caption. If it actually looked at the image, it's going to do pretty well. Okay, so there is our ground truth. Any questions so far? All right. So as I'm very happy to learn that TCAV score matches with ground truth pretty well. So this blue is accuracy, and the green line is TCAV score for images. And you want to see roughly blue line with hanging out with a green line. And here, this is a different class. You see the accuracy is like right here. It looks pretty high, but it's actually random because there are 3 classes. 33% is random. So this is pretty low. And it looks like TCAV image score matches. So maybe, but being like, that's cool, but like maybe this case was so simple and it's a toy example, maybe saliency maps can do it too. Maybe. So we tested that. We have four different methods, and we have testing images without captions. And remember, none of these models looked at the caption. Captions are not important, right? However, a lot of saliency maps looks at the caption. Oh, caption, oh, caption, oh, caption, right? So that sounds problematic. But maybe you cherry pick this picture. So we did Turker's test. We hired 50 Turkers and asked, given these two series of pictures for 3 different classes, do you think the image was important or the caption was important? The findings are pretty interesting. So remember there are 2 concepts, right? So you pick one or the other. Random is 50-50. Humans do 52%. So they can't tell. They can't tell whether image was important or caption was important. And they're always split in half. Half of the Turkers were like, oh my God, it's definitely images. Half of them were, oh my God, it's definitely captions.
All of them just randomized. Maybe all of them they are just flip a coin.
Terrible.
Yeah.
We do pilot question. This is actually a really important question. Turkers' quality can vary, as you may know. So you have to do this pilot testing before that to make sure they understand the task. They're not randomly clicking it, and they are optimizing for the performance. So we give them, like, if you get these answers right, we'll give you like 20%, $20 more. It's important. Something that I find it fascinating, though, from this Turkers experiment is that people are so confident. Whether they're wrong or right or incorrect, 40% of Turkers said, I am as confident as I will ever be. And they answered this question. And this is not just Turkers. I actually see this symptom over and over again. If you see something you like and you think you're right, of course you're right, then you like it. And you have like boosting confidence on that answer. This is exactly the confirmation bias that we should be careful for. This is why we need to be very careful of taking into account our feature, human's feature, which is these biases. So we got excited after this sanity check experiment, and we ran TCAV on 2 widely used image prediction models. And we ran a bunch of different concept sets. 1 color, race, and objects. In fire engine, the red concept and green concept were high. Green was high because a lot of fire engines were sitting on the grassy field. And that sounds good to you, right? Red fire engine. Unless you're from Australia, Canberra. Anybody from Australia? Oh, are you from Canberra or no?
I lived in Canberra, yeah.
Oh, great. I met actually someone who knew exactly where this picture was taken from. There's like a 1 fire station or Canberra.
Yeah.
So there's a good reason actually why fire engines should be yellow, because at night, yellows are more visible than red. Right? So apparently, it's like some psychologists argue that we should have a yellow fire engine, but we just
Australians are smart.
Yeah, there you go. So this might be showing you some geographical bias, the countries where fire engines are red. If you remember the very first Deep Dream blog post, where they discovered this neuron that shows a muscular arm. And they conjectured that, oh, maybe when predicting dumbbell, muscular arm is an important factor. Then now you can quantitatively verify, yes, arms were important. And in this case, I didn't have arms data set. All the other data set, I got it from a publicly available race data set. So I went onto Google image search, and I searched arms, and I collected 33 images, and it passed statistical testing, at least for this layer, and got the answer that was consistent with prior literature conjecture. So perhaps going back to our goal that we started to talk with, perhaps this tool can help you to see whether your values are aligned in your model. Now, really excited with these results, we went to doctors. We work with doctors who study diabetic retinopathy. Diabetic retinopathy, or DR, is treatable if you discover early, but too late if you discover a little late and you lose your sight. So we have a model in medical brain that can predict DR level pretty well, like 85%. And our question was, well, but is it doing it in a way doctors would have done? Because we want to eventually deploy this model to rural areas where there are no doctors. So we went to a doctor she told us what kind of concepts that she would look for in DR level 4. This is most severe level DR. Oh, thank you. And then we went also asked her, what are the concepts that you don't look for? And we did the same thing for more mild level of DR. Now, of course, we have images that are associated with these concepts. So, and then we used TCAV to ask the model, what do you think? For model DR level 4, where prediction accuracy was high, the model said, yes, I am doing something that doctors would have done. Red is low, something that doctors don't look into when they look at this class. Green is high, good story. Story is a little different when the model has mediocre accuracy. It turns out that when model has mediocre accuracy for this DL level 1, it's looking at a concept that doctors would not look at. So we dig this farther, and we realize that the model often confused with level 1 and level 2. And level 2 has a lot of HMA. And they realize, oh, our labels are noisy because doctors don't really agree with each other what level it should be. And that might be hinting you that perhaps using this tool, you can figure out whether your domain expert knowledge is well reflected when you want it. So I talked about TCAV. This is a way of giving you whether the concept of your choice was important or not and how important they were, if and only if the network learned about that concept. So here's some self-promoting slides. I've been really thrilled to see responses from inside and outside of academia about this work. Sundar talked about this work at Google I/O, and I was honored to go to UNESCO Center in Paris to receive one of the awards, and as selected as one of the 10 cutting-edge technology. And inside of academia, Carrie Kai worked on this paper of helping doctors sorting medical images with respect to the concepts of their choice, so using their language. And this paper was part of a Best Paper Honorable Mention in Kai conference this year. A couple weeks ago, I met this Eric, who works at Aerospace Incorporation, who used TCAV to interpret storm prediction models. So Cat 4, Cat 3, they based on concepts like eyes of the storm and so on. He was able to interpret this model. That's somewhere helpful. Another student in Switzerland, she extended TCAV to regression models and worked with doctors for breast cancer and was able to confirm also this is useful. But I see this work as really a way, like a white canvas, really, like what you're saying. There's a lot more things that can be done. So saliency map method, there's a first paper, I think 2009, by Dumitru Orhan, who is now at Brain. He put out this paper on using the first order gradient with respect to pixel. And then there has been a lot of great work following that, trying to do like even better things and some other things. So I think of TCAV as a first branch of this new direction. And therefore, there's a lot of limitations that I would like to spell it out to you. So concepts in TCAV has to be expressible using examples. So if you want to express concept of love, I'm not sure how you can do that. Also, concepts has to be provided by human experts or the users. You need some examples. While the number of examples might be pretty small, what we discussed, what we find out, 15 to 33 is giving you pretty good results. But some domains, maybe that's not enough. Then you have to go get your concepts. I think there's a lot of exciting work that can be done for discovering concepts automatically. We did some work for images, but I think there's a lot more great way to do this. Of course, TCAV is not causal. In fact, a lot of interpretability methods are not causal. It's completely correlation-based. So developing more proper causal way to discover concept, attribute to concepts or pixels would be useful. We also did some work, but we realized that computation complexity is pretty high with causal methods. If you have more ideas, I'd love to hear. So lastly, what sort of things should we be careful in our journey? I think it's incredibly important to do proper evaluation. We should check, even for the simplest case, that we are doing the right thing. If it doesn't do the right thing in the simplest case, we are wrong. We should go back to drawing board. And including sanity check or some other ground truth-based evaluation, we should be doing this so that we can focus our effort to go somewhere together. Test with humans. The final consumer of your method, the only reason your method exists is for humans. So if you don't check with humans, that's as if you designed a beautiful, trained a beautiful classifier, and you never checked on test accuracy. have to check with your humans. Remember, we're biased and irrational. Great book that I love is called Undoing Project. Probably a lot of people in the audience read it, by Daniel Kahneman. Really love that book. It goes into what kind of different biases that we have and how that's so profound in our ability to reason. We're totally biased, very irrational, and we need to take that into account when we're designing interpretability methods. Talk to your HCI experts. The fastest way to fail interpretability method is to have a bad interface or bad workflow. It will not work, I guarantee. So work with HCI experts to get their help, need their expertise to get that part working. I'd love to hear your criticisms. Of course, it's better if it's a constructive. And hear about where we can go from here. What do you not like about this direction that I suggested? What can we do better in TCAV? There are plenty. And let's make sure that we're going to the right direction. Let's keep in mind that the goal is to give a tool, for me anyway, that is useful for people so that they can be responsive in the way that they want to. With that, thank you.
We have time for one or two questions while the next speakers gets up. Questions?
Thanks. Wonderful talk. Have you thought about combining domain expertise with interpretability? So for example, you have a concept that the doctors are using. Potentially you can incorporate this into the loss function and then gradually phase it out to give the model maybe a warm start.
Yeah, really good question. The first thing my doctor of DR said was like, oh, now it's speaking my language. I can talk to it, right? Can I tell it that it's doing the wrong thing? We would love to. We have some initial work, but I think a lot more work needs to be done. We need more HCI experts to actually nail that work. But really important.
Yeah, have you thought about actually using the interpretability score itself as a means to train better models, somehow incorporate it into the objective function?
Yeah, really good question. We are doing a little bit like version of that, like that type of adversarial training. So for example, if you don't want a layer to be sensitive to a concept like race, then you can make sure that it's not sensitive, the gradient is small. So we are doing like simple form of that, but I think there's a lot more work to be done.
I think we're going to stop. So thanks again.